Hello everyone, my name is Celine Mawad and this is my Physics 2211 Lab 2. This lab consists of modeling and analyzing the motion of a falling object. For this lab, I used a calculator falling down in the negative y direction from a particular height. Then I used Tracker, an image tracking software to record the movement of the ball in function of time. In addition, I relied on GlowScript, a computational program to simulate the movement of the ball and predict its motion in the presence of the force of gravity and in the presence of both gravity and drag force. Comparing the observed motion to the expected outcome allows us to see how well the momentum principle or Newton's second law can be applied to the system by considering the effects of different forces. The results show that the computational data that includes gravity and drag force more closely resemble the observed data than does the predicted data with only gravity. Let's first start by defining Newton's second law. According to the momentum principle, the net force can be calculated by dividing the change in momentum by the change in time. When there is no net force acting on the system, its velocity remains constant with maintaining the same speed and direction. When there is a net force acting on the object, it will cause a change in its motion and velocity. The first step consisted of taking a video of the system, in this case a calculator falling from a particular height. Using Tracker, I set up the center of the ball as the origin of the graph, and I oriented the y direction upwards. I used the calculator's dimensions to specify the length scale. The different positions of the center of mass were recorded between time frames 16 and 59 and represented in a table and a graph as you can see on the right. I relied on the data obtained in order to use them for my computational model. I noted the initial position vector at t equals 0 seconds and the final position vector at t final equals 0.726 seconds. The next step consisted of using the computational model GlowScript. I made some edits to the starter code by inputting the data obtained from Tracker. I changed the calculator's mass, its initial position vector, and I set the initial velocity vector to 0 because the object starts from rest. The magnitude of the acceleration due to gravity on Earth is 9.8 meters per second squared, and g hat is the unit vector for the positive y-axis that is used for calculating the weight and drag force. In the first model, drag force is not included, so the drag coefficient is set to 0. Then I plug the final time into the while loop. Fnet is only equal to the weight force acting on the system. The object's velocity and position formulas were also modified and derived from the momentum principle. Finally, for drawing forces arrows, I set the arrow scale to 2.267 corresponding to 2 meters divided by the magnitude of the weight. Here are the results of the GlowScript model for only gravity acting on the system. Next, I constructed a second computational model that includes both gravity and drag force by keeping the edits made in the first model. I input the proportionality constant for the magnitude of the drag force by running the code over and over until I reach the same final position as in Tracker. Also, the net force is now equal to the sum of the weight and drag force, with its formula set to b times v squared times g hat. Here are the results for the second model after running the program. The following graph of y position versus time was obtained from compiling both observed and Model 1 and Model 2 data by using Google Sheets. As you can see, the experimental and predicted model with weight and drag force are mostly similar. There is a bit of underprediction in the middle that can be due to error in capturing the center of mass in Tracker. The predicted Model 1 curve diverges from the experimental curve and is way below it because the acceleration is increasing with no force acting to slow it down. Overall, Model 2 is much more accurate than Model 1, which reflects the correct assumption and consideration of the drag force acting on the system. Terminal velocity is reached when the force of gravity is balanced by the drag force. In other words, the net force must be equal to 0 and the velocity is constant. Since the slope of the graph corresponds to the velocity, the slope should be constant and not change. As you notice from the graph, Model 1 will not reach terminal velocity since its slope is not constant, while the experimental data and Model 2 will reach terminal velocity because their slope is starting to flatten. If we take the case where the object is initially thrown downward or dropped from rest, we see that the terminal velocity will be the same. The left graph represents the object's velocity in function of time when it is dropped from rest, while the right graph shows the velocity when the object is moving at velocity of 3 meters per second. We notice that the terminal velocity is reached at the same time regardless of the initial velocity. This is it for my presentation. Thank you.